Thank you everyone for coming. It is an absolutely crazy time all around the world, but perhaps especially in America right now. I hope everyone is doing well. Thank you. Okay, so this is some joint work that I did with Austin Blatt, a former undergrad of mine who's now off in industry at Puppet Labs. So, you already know what my talk's about, but I want to sort of frame it appropriately for you. I am interested in powerful programming languages. That's why I got into PL, that's why I got into computer programming, was this feeling of power, among other things. And so when you see powerful programming languages, you probably think about systems languages, C and Go and Rust, and maybe even Java you think of as powerful. I don't know, people have different tastes here, Haskell. All those are really wonderful, powerful languages, but I want to ask you, if a language is so powerful, how much damage could you really do with just like one line of C? Like, what are you going to do? Like, what could you possibly do to your system? You might corrupt memory, but that's just that process, right? Really not so bad. If what you want to do is some really serious damage, if you really want to destroy your computer, that is to say, if you want a language that's powerful, what you want is the shell. Okay, so this talk is about the shell. I wrote a new POSIX shell called smoosh, and this talk is sort of all about that. If you don't know POSIX, I'll talk about it a little bit more. It's a open spec that ranges from like ABI all the way up through user utilities and the shell and things like that. C functions, all kinds of stuff. Smoosh, I'm hoping will be a foundation for you to think about and use the POSIX shell. Okay, so just like to spill it all up front, what am I going to talk to you about today? These are sort of the 5 takeaway points that I'd like you to have at the end of the talk. So first, that shell is powerful. Hopefully needs no real explanation, but I'll talk a little bit about its power. Shell is misunderstood. I think this also needs very little explanation. Everyone's tongue is sort of halfway in their cheek whenever I start talking about the POSIX shell. More seriously, the shell has interesting modal semantics. And I'll talk about what I mean by modality here, but I think this is just sort of an interesting difference about the shell, and I'm interested about why the shell is so different from other languages. On the topic of my own work, I want to convince you that Smoosh's tested semantics, which is the way to go here, lets you reason symbolically about shell scripts. So I think this offers some power for sort of taming the shell's own power. 2 other things I want to tell you about. One, POSIX compliance is a phrase that people sort of throw around quite a bit, but what precisely that is a tricky thing to grab hold of. So I want to poke at that a little bit. And then lastly, that smoosh has already been useful. So smoosh finds bugs, it finds bugs in other shells, and it finds bugs in the POSIX test suite. Okay, so that's a general plan for today. We're going to go through quite a bit. I need to start actually with an apology. It's not the apology you think. You might think, oh, this is the apology he makes for working on the shell, and I actually am not apologetic at all. It's apology for, I'm going to spend a long time introducing things. So the quote here is from Jonathan Swift's A Tale of a Tub, which begins with like 60 pages of introduction. The whole time he's apologizing for how long his introduction is. It's like medium funny. And I have the same problem here. I have about a dozen slides where I'm just going to like frame what I'm doing. Okay, so like people have passionate opinions about the shell. And I really want to be careful about sort of setting the scope, so just so that we're all on the same page about what I'm talking about. So I'm sorry that it's going to go a little slow. I'm a little bit heartened that it goes a little slow because these 2 sort of emblematic symbols of slowness, the snail and the turtle, both have shells. So obviously I'm onto something. Okay, so the POSIX shell. There's this open group spec, right? This is like, it's like an institute that does specs. And it also is an IEEE spec. The current one is 2017, a new one's about to come out, and like there'll be new features and bug fixes. Like it's a living standard. The shell spec itself is intimately connected to the rest of the POSIX system, right? So if you look at the documentation, everything's interwoven. Like it's talking about the C API, it's talking about other utilities, it's sort of all over the file system, it's all over the place. There are many implementations of the POSIX shell, some more POSIX than others. Bash is probably the most widely deployed. It has lots of extra features. And in fact, if you want it to be POSIX compliant as best it can, you have to ask very nicely. Dash, which I've highlighted in bold here because I sort of take it as a model, is a simplified version. It's used in the Linux boot sequence and elsewhere. We'll follow Dash if I'm going to say a behavior and it's not uniform. Okay, so that's the POSIX shell sort of like from these 2 perspectives. We'll return to these 2 perspectives. By way of framing, shell is ubiquitous, right? If you're gonna manage a system, even these days, not quite as much, but still even on Windows, the POSIX shell is I think one of the main games in town. It is a near universal tool, certainly for Unix system administrators, and sometimes it's the only way to accomplish tasks. So it's a ubiquitous and powerful tool. Shell is unique. It's really not much like other languages, right? It's its own thing. I've highlighted these 5 points of what I think are its most distinctive characteristics. So first is its unique evaluation model. It does expansion, not evaluation of arguments by default. I'm going to explain what all that means. I think it's one of the best languages today for deploying and managing concurrency. I'll talk about this a little bit more in a second. I have an example I want to show you. It's a programming language, but the scripts that you write in the shell are really human automation. When you write a shell script, it's running the commands that you would run for the most part. It's just doing it faster. So it's almost more akin to like macros in the like Microsoft Word sense than it is sort of conventional programming languages where you build data structures and do things in ways that a human wouldn't do, but are the efficient way of doing them. So that to me is interesting, that they're automating human tasks. And then lastly, the programming model and the shell's general use case is this sort of uniquely interactive model. There's this try before you buy approach where people will like write loops and then have an echo in the loop to say, well, this is the command I would run. Is this what you want? So this is sort of interesting. This is not how I think people normally write programs, but it's how they write programs in the shell. If you don't think the shell is unique, that's fine. I just invite you to try using, say, Python as your shell for a day and let me know. Okay, I want to dig in a little deeper to this concurrency topic because I want to motivate the shell as like actually in some ways kind of good. This is part of why I want to work on it. So here's a script drawn from actually a paper I did with Kathleen Fisher and David Walker back in 2015, where we were doing topic modeling of programming languages literature. It's a fun little paper. You can sort of see trends and stuff like that. So we used the LDA tool, latent Dirichlet assignment. It's like a way of finding topics in text using natural language processing. And I wrote some script that does something like this, like you have to choose how many topics you want, and we're gonna run a bunch of them, and you run the tool. So there's a for loop. I don't think you can see my mouse, unfortunately. So there's a for loop. You run LDA on the appropriate setting K, and then you tell Git to not look at those files because they're huge. And if you run this program, you'll get something like, okay, well, I'll run the K equals 50 cases, first the LDA, then the echo. And then I'll run the K equals 75 cases, the LDA, and then the echo. And then the K equals 100, and the K equals 125. Right? You'll just run all these scripts. Okay, I just made it concurrent. What did I do? To make it concurrent, I just added that little ampersand at the end of the LDA line, and I added the wait at the end. So for those of you who are into concurrency, that's a fork, and that's a join. So you may not think of the shell as having fork join concurrency, but in fact it does, and it has, I think, a superb syntax for it. So now just with this tiny change, right, including new lines, I think we're talking 11stein edit distance of 7. Now we have this nicely concurrent system. And moreover, LDA is a sequential program, right? It'd be cool if it were threaded, but it's sequential. So like we're freely kind of mixing sequential and concurrent code, right? If LDA were threaded, all of this code would work exactly the same. We wouldn't have to worry about pooling or whatever. All that kind of gets managed by the OS. And then what's more, it's all sort of inspectable, right? You can use PS or top or htop or whatever. You can kill individual processes. This isn't sort of monolithic. Like you can interact with all of these things you've spawned up. So to me, this is really interesting. Like what a powerful system for handling concurrency. So I have a paper at DSLDI 2018 that explores this topic in greater detail that you can check. Okay, the other area I want to highlight, and then I'll move on, is that the shell offers a sort of continuum interactivity, right? On the one end, you have what most people do, right? This like purely interactive use. I'm just going to run command at a time to move around and manipulate my system. And on the other end, you have things like old system V and its scripts and like serious system script software that are like the things that keep servers running. And it's really interesting to me that there's also middle ground, right? Like you can, if you're the right kind of person, write loops on the command line to do little quick scripts, or you can write a more serious script, like maybe migrate that loop on the command line to a more serious grading script or something like that. And this is the sort of thing that I certainly do all the time, and I know other people who are even less into the shell than me do it too. And it's really impressive to me that a single language can accommodate all of these cases. So those two features, the concurrency and interactivity, seem like really unique positives for the shell. They're part of what sort of make me really enjoy the shell and want it to be better. But I would be remiss if I didn't point out that the shell is also unique in like the not good way. So there's I've highlighted two things here. Up top is a real bug classic Steam bug. People called it steam cleaning, where basically if you configured your volumes right for Steam on Linux, it would delete all of your files. So that sucks. That's not a thing you want. And in fact, that comment's scary. The line down there, scary. That's in the original source code. Like, they knew what they were doing was dangerous, but they thought it was safe. But like, they just couldn't quite reason through the sort of bunging that they were doing up at the Steam root. Like, it's possible for that to end up being empty if you do it wrong. Okay, so that's like a nasty bug, right? This is where the power and the misunderstanding quality of the shell become particularly dangerous. But then also there's a more prosaic, like, here's how Puppet, the people who like arguably are trying to replace a lot of shell stuff, say, oh yeah, here's how to install our software. And here's how to do it. And that like pipe to bash is just a huge yikes to me. It's a yikes on a low level where it's like, you should write it to a file and then run the file. Because if you get interrupted midway, bash will run like half of your install script. And that's bad. But also just like, you're not even gonna look at it? Like, maybe we should look at it. So like, one of the motivating goals is like, well, can I put something after that pipe that sort of says, and does it look good to you? Does this seem like a reasonable thing to run? Okay. So that's sort of the shell background. I want to talk a little bit about related work. This is a bunch of unrelated work. I don't particularly want to dwell on it. Maybe you see names that you recognize. People have done a lot of cool stuff related to the shell. I don't think any of these things on this page are like close to what I'm trying to do. Like, they're all working on stuff related to the shell, but they're just not it for me. There's 3 pieces, I think, of actually related work. I'm happy to revisit this at the end or chat about it with anyone who wants to. There's Carl Mazurak and Steve Zanswick back in 2007 published a static analysis for Bash, not the POSIX shell. And I think it's a lovely start. It doesn't cover all the features you'd want, and it just needs to be bumped up. So I think that's a cool thing. And then there's a group at University of Paris, Diderot, Ralph Trinan's group. And they have built their own from scratch parser called Morbig, and I'm gonna adopt it. I think it's great. And then they have their own approach, which is sort of like a mini shell, like a core calculus Colli that has shellish features, but is sort of miniature. And to me, that exactly inverts my priorities. I'd rather have a core that was sane, right? Like was just like a functional programming language or some simple imperative language. And then I have some primitives that I can reason on top of that sort of implement the other things. But I don't want the semantics of my core language to look like the shell. So Colli is cool, but it kind of inverts my priorities. There are other people working in the POSIX spec space, just not on the shell, notably Philippa Gardner and her student John Insick, and Peter Sewell's group on the REMS project. And I think there's some other people like who touch on these topics. Okay. Whew. That's the introduction. A little long. So in the rest of the talk, I'm actually going to tell you about what I'm doing. I want to talk a bit more about the shell in general and smoosh in particular, why it's a good model for the POSIX spec, how it's built, some of the problems I encountered in implementing it, and where I'm headed. Okay? Okay. So this is what smoosh looks like. Right? So smoosh is a semantics, which has sort of 2 holes in it. Right? There's a hole up top that says, okay, how would you like to use this semantics, right? Like, tell me what terms you want to step. And then the hole at the bottom says, okay, what are the operating system operations? Unlike many other programming languages, or really most other programming languages, the semantics of the shell itself, even for simple structures, demand OS system calls, right? The semantics is in terms of system calls. So it's really critical to understand what does the OS look like. So the way you plug these holes sort of determines how this shell will actually run, and you get to sort of choose your own adventure. So in these diagrams, there are other things in these holes. Let me talk about them a little bit. There's expansion and evaluation. This is the modal semantics. I'll talk about those in greater depth in a little bit. You also have like the built-ins. So like there's shell operations like CD, PWD, echo, test, right? All these need to be sort of built into the shell. So that has to be in there. Then there's the POSIX definitions. What is a signal? What is a job? How are you tracking jobs? What about file descriptors? Like all of these things need to be sort of managed. And then lastly, you of course also need a parser. So I use Dash's parser, which I've wrapped up in a library that I call libdash. And I've highlighted the bottom part of that in red to make it clear that that's unsafe code. It's written in C. And anything I show in red here will represent sort of unsafe or foreign code. Okay, so what can fill in these holes? Like what goes in there? So I've implemented 2 modes so far. One, system mode, fills the top hole with sort of a conventional shell driver. It's about 200 lines. Most of it is just parsing command line arguments that sets up something that like reads the input from standard in or whatever the shell's supposed to read from, and then steps it and then gives you the answer and then sends you a prompt. It sort of does all of the ordinary shell stuff. And then the way we fill in the OS model is by giving real system calls. So I've highlighted it in red, even though it's written in OCaml, because it's making like legit system calls. So like these could of course fail. You know, they're talking directly to the kernel. It's low-level systemsy stuff. So when you're in system mode, smoosh is just a shell. You can run it. You can like run any of your scripts you want in it. Use it interactively. It doesn't have readline support, so it's maybe not the tool you want for your day-to-day shell use yet, but it certainly is just a working shell. Okay, I can keep the same semantics and swap out what goes in the holes for a purely symbolic mode. So here what I do is I have, you'll notice in orange, not red, a model of POSIX. So in my model, I handle file descriptors and FIFOs, and I have processes, and I do all the scheduling. It's a purely symbolic model of a POSIX system. Where you won't actually touch the file system at all, right? You're not going to actually hurt your computer running programs in symbolic mode. And then the driver that I've written for this one is called the shtepper. What it does is basically output some JSON that says, hey, here's my current state after every step. And then I use that to drive a web interface that I'll show to you in a little bit. Okay, so this is the same semantics, right? It's exactly the same core. I'm just using it in a different way. Okay. When I say that smoosh is a foundation, my hope is that you all can find other things to plug into these holes, right? Maybe you have an analysis, right? You want to do taint analysis for, you know, how user inputs are being used in a shell script, or you want to rebuild Mazrak and Stanowicz analysis, ABASH, but for the POSIX shell with all of the features. So great, you plug in a different hole up top, and then maybe you just use my OS model, my symbolic one, right? That's perfectly good. Or maybe you have a different model you want to use. You want to run a shell that'll be harmless but real. So you want to write a read-only OS model that only makes safe system calls and sort of only reads from the file system, never actually writes to it. Okay, great. You can keep my shell driver, but you just write a different OS model, and now you have a safe shell that you can run scripts in, and it'll sort of just log what it would have done without actually doing it. Okay, cool. So that's the general architecture of smoosh. I want to talk a little bit about shell semantics. So most interactive languages have a read, evaluate, print loop, where you do parsing and then evaluation. The modal evaluation in the shell means that there's an extra step in the middle called expansion. So expansion is this sort of the stringy part of shell evaluation. You may not have heard the term, but you've certainly felt and seen its effects on the shell scripts you've written. So I've highlighted over here on the right, right, your left maybe, impossible. So I've highlighted over here the 7 stages outlined in the POSIX spec of what expansion are. So there's a short program on the left and then an arrow to sort of what it expands to or what it produces on the right. So the top 4 are sort of the easiest to think about, clearest notions of expansion. So there's tilde expansion, which says that tildes map to user directories, and if you don't say which user, it'll be the current user. Then there's parameter expansion, variable expansion. That's when variables get turned into their string values in commands. Then there's command substitution, which uses backticks or $paren for running a command and capturing its output. I'll talk about that a little bit more in a second. And then there's arithmetic. So this is the $paren, and this does arithmetic evaluation. Okay, those 4 are like expansion in an obvious way. Like they take the command or the text of the command and they expand it to form a new command and run that one. There are 3 other stages in the spec that get called expansion, but are just kind of something else, right? They're just like stages of the stringy manipulation. So the next example is demonstrating field splitting. So IFS is a shell variable that controls how fields are split. You have almost certainly encountered a bug related to field splitting. Field splitting is very hard to wrap your head around. It's sort of what breaks strings up on the command line. The next one is path name expansion. So this is globbing, star, question mark, like the character ranges and brackets, stuff like that. This is also when Bash would do the curly brace expansion. And then lastly, there's something we call quote removal, which is just sort of getting rid of any quotes. The quotes were there to control field separation. Okay, So those are the 7 stages of expansion. Hopefully they're more or less familiar to you. I want to dig in a little bit deeper to command substitution. So what's really happening here? If I run the command base name pwd, the shell will expand to something like this, depending on the directory that I'm in, saying, okay, well, this is the real command I'm going to run, base name, and then whatever the result of pwd is, and then I'll get whatever base name does. So I've color-coded it here and throughout the talk, where pink is expansion and blue is evaluation. So what's really happening? How does this work? Well, when you do the backtick pwd, a new subshell is created to run the command pwd and to capture its output. So the command pwd will sort of nestedly be expanded itself. It expands trivially because there's no variables or anything to do anything to. It runs, and then we capture the output, and then that output is plugged back in as part of the expansion. So there's this sort of nested modal evaluation where within the expansion mode, we could have expansion and evaluation happen again. Diagrammatically, that means something like this. This is your general loop of how the shell evaluates, but then within expansion, I could run another set of expansion and evaluation, and so on. Okay, this is part of what makes the shell hard to reason about. So I want to show you a tool that I've built to help you. Okay, hopefully you can now see my desktop and this bad boy. So this is the shtepper. I'm going to use the live tool, which is probably a bad idea. But here we are. So this uses the symbolic mode to tell you how a shell program evaluates. So you write the shell script here. You give it the starting environment and sort of some other information that it needs. This is sort of simulating the contents of etc password. And then what it'll do is it'll step you all the way through. So it's going to show you expansion steps with legends in pink and evaluation steps with legends in blue. And these bits are for explaining how the various bits of expansion work. So let's look at what this program does. Let's make a prediction before we do it. So I assume someone would have interrupted if you can't actually see this screen. Yeah, they don't show you what you're sharing. So
we can see.
Thank you. Okay. So this program is going to print out, well, first this. Now this is an expression that says, give me either the value of x, or if x is unset, could you please set it to 5 and then give me the value? So because x won't be set down here, it'll get set to 5. And then this is arithmetic evaluation, which says, okay, x plus 1. So that this should be 6. Worth noting, if you're not a serious shell programmer, that we don't need the $sign here. Inside an arithmetic expression, you can just use variables without their dollars. It also works to use the dollars, but in a more complicated way. Okay, let's run it. Okay, cool. So by way of legend, we're going to go through a couple of different stages. We'll start in gray, totally unexpanded. We'll run those first 4 stages to get to expanded words. We'll do field splitting to get to temporary fields. It's right before we do the globbing. And then we'll get to fully expanded fields. These are just strings that'll tell us what the shell is actually going to execute. So let's see what happens. So we start out evaluating. We're going to evaluate this. Oh, it's a simple command. I need to expand the command args. Starting expansion. Okay, so now we switch to pink. And we're just going to expand it just word by word. So we expand echo. It expands to itself. We expand the space. Expands to itself. Says it's a field separator. It's a user field separator. This matters, right? Separators that come from further expansions are different from ones that the user entered. Okay, over here, it says, okay, we're currently trying to expand this because X was unset, so I need to set it. Okay, so after that step of expansion, we get to this point, and then Smoosh will show you your environment again because it updated, right? It changed. Okay, keeps on going. We get to the arithmetic expression. It expands the text of the arithmetic expression first. Then it evaluates it, right? Computed arithmetic result. I do that in just one step. I figure we're all adults. We don't need to see precisely how every step of arithmetic worked. And then we get here. Okay, cool. So those first 4 stages of expansion have completely happened. And we've gotten to echo 5, 6. Now, there's nothing else interesting here for field splitting or path name expansion to do, so these two steps are more or less immediate, right? Field splitting, path name expansion, and quote removal all happen immediately, and we get here. Okay. They're done expanding any assignments. There aren't any. The assignments are expanded, and now we're ready. This is the command we're actually going to run. Echo with the first argument 5 and the second argument 6. And then here's our simulated standard out. 5, 6. X is 5. Okay, brilliant. I had a couple other examples I wanted to do. Okay, so here's an example about tilde expansion that just shows you how tilde expansion works and how you're allowed to do it. So this says, okay, show me the path to root home directory. Then set a variable USR, user, to root. And then let's see if we're allowed to use this indirection here. Am I allowed to store the username in a variable? I'm going to give you a hint. The answer is no. So if we run it, we'll get here. We'll expand echo to itself, field to itself, and then tilde expansion tells you the home directory. Keeps going. Okay, great. The first command outputted. You might wonder, well, wait a minute. That's a bug. What happened to your other commands? But the shell is line-oriented. Each line, each command runs, and then the next one is parsed. It doesn't parse the next one until the first one's all the way running. Okay, this variable assignment is pretty uninteresting. You may note that I'm sort of giving a lot of information for something that isn't so interesting, and that's just because the shtepper, tries to err on the side of giving too much information, but it's not all the way there. Okay, now when we get here, so you'll notice this tilde didn't expand. Said it was just a plain string. And this is just because of the way the POSIX spec says this is supposed to work, right? The tilde prefix says, oh, if I'm not followed by a colon or a slash, don't treat me as a tilde for expansion. This indirection should not work. So you'll just get tilde root. Okay, so another tricky expansion case. And now I want to show one last one about, well, maybe we have time for 2. Where are we at? 9:30? Oh, we have plenty of time. Let's see how we go. So this is a program that that shows how field splitting works, what's really going on. Oh, let's get rid of that fancy quote so we don't get a parse error. Okay, so count is something that will just show the number of arguments it was given. Here is a variable x that says, I like snails, love snails, delicious. And then I'm going to call count in 2 ways, one with just $x and one with quote $x. Okay, so we define our function. We set our variable x. Okay, so let's look what happens for the first invocation, count $x. We expand count, expands to itself, and then x expands to all of these words with spaces. Okay, now field splitting is interesting. The spaces here, these tiny spaces here, turn into field separators. So then count will get called with these 4 arguments. So asking the number of arguments will be 4, and it'll print out 4. Now, if we quote it, what happens? So again, it expands to these words, but field splitting treats it differently. Field splitting retains the quotes and treats it as one single unit. So then when we call count, we're going to call it with one long string with spaces. So count, when it runs, says, oh, I only got 1 argument. So at the end, we get 4, 1. Okay, so this is what's actually going on with quotes, is you're controlling field splitting. You put quotes when you don't want spaces to be broken up, is the rule to use. Okay, one last thing just to demonstrate that my POSIX simulation really does what you expect it to do, sort of simulating pipes and everything correctly. This sets up a pipe. There'll be 2 processes. The first process will just send 10 on standard out. The second process will read it in and then show the result of multiplying it by itself, by squaring. So unfortunately, we're not going to get anything good because we're just going to see what this second one does. Oh, excuse me. We're just going to see what the main shell does. Each of these becomes its own subshell, each of these subprocesses. So we're just waiting on 2, the second process. I'll talk a little bit more about how all this works in a little bit. So I have the information. I'm just not giving it. I'm not displaying it in the shtepper, but we can see that it gives the right answer, right? That we're successfully sending information along a FIFO. Okay, so hopefully at this point you can see that the shtepper is a tool that lets you see what's up, lets you understand what's going on in the shell. What I want to do next is give you a higher level formal view of what the shell does, talk about the formal model of how the shell works, talk a bit more about my implementation, and then we'll talk about POSIX compliance and my future work. Okay, so this is the AST for the shell. It's really not as bad as you think. What do we have? So unfortunately, you can't see me gesticulate wildly in what someone once called the hyperkinetic Greenberg style. So I'm just gonna go one by one and hopefully it'll be clear because you can't see the mouse. We have simple, on the first line, we have simple commands with assignments and commands. We have redirects, that R is a redirect. Then we have pipes, asynchronous commands or background commands, and subshells with parens. Then we have some logic flow of control with double ampersand for short circuiting and double bar for short circuiting or. We have negation, we have sequence, we have conditionals, where the exit status of the C1 of command 1 tells you which one to take. 0 means true, everything else means false. We have switch cases, conditionals. And I should be very clear that this is not exactly the concrete syntax of the shell. We have while loops. We have for loops where you enumerate the characters in a word, or excuse me, the words in a word. And then we have function definitions. So there's some shell specific stuff here. The pipes, the ampersands, the subshells. The for in loop is like a little funny, it's a string loop. But overall, the language is pretty sensible. Until you dig into what exactly is W? What is that? What does that symbol mean? Ignoring the W, this seems like a perfectly easy to think about AST. So W is words. So the expansion, what I've been calling expansion, is really properly word expansion. So words are a mix of strings drawn from whatever character set, ASCII, UTF-8, or whatever, and control codes. So control codes are things like tildes and variable references and backticks and arithmetic things and quoted things, right? All these are control codes. Notably, star is not a control code. It's dynamically detected. So there's like a bunch of what these things can be. I'm not showing all of them here. And this is sort of a model of what a string that could be expanded in the shell looks like. So if I input something like this, right, however many spaces, really we're gonna get out a string that looks like this. There's two statically known fields here. There's ls, which is a plain string. Then there's a field separator. Doesn't matter how many spaces they were, it's just a separator. And then there's a mixed string with some control codes and some string characters. So tilde is a control code, $x normal, right? That's just like a $x, just referencing a variable. That's a control code, but slash, right? That's not a control code, that's just a string. The star, that's just a string, not a control code. Okay, so these are what undergo expansion. What does expansion look like? Expansion is a 5-stage process. You take your user input as words. You expand all the control codes. That's these Ks, the tildes, the variable references, the backtick subcommands, the arithmetic things. And then you get to expanded words. That's in orange. So expanded words have done most of the expansion, but not all of it. I have to keep track of, okay, is this string from the user or was it already expanded? Because those need to be treated differently. Is this a list of fields that came from the $@ variable, which gets treated specially? And then I need to keep track of quotes because I haven't yet done field splitting. Okay, then I'll do field splitting, but I still need quotes because it's going to affect more. And then I'll get to what are called intermediate fields. And there I just basically keep track of 2 different kinds of word separators, and I keep track of strings, and I keep track of quoted strings. Okay, then I'll do globbing, and that just takes intermediate fields back to themselves, still in green. And then I'll eliminate the quotes, and I'll deal with all the field separators, and then I'll just have a list of strings. That's called fields. Okay, so that's how you go from words down to fields. I should be very clear that the POSIX spec really only talks about words and fields. And then it's kind of up to you about what happens in the middle. So in my code, which is a small step operational semantics, I literally do small steps to slowly expand all of this, though some of the later stuff I do is functions, like globbing is more of a function. But something like dash or bash, like this is just some mutable structure. It's some string-like array or rope or something in memory, and they mutate it. That's what they do. And then the POSIX spec doesn't tell you how to do that, right? The same way the POSIX spec doesn't tell you how precisely you're supposed to compile, individual C constructs or whatever, or the C spec POSIX. Okay. I should point out that this is itself sort of a pretty recursive process, right? Like we already saw that expansion evaluation can happen itself in expansion, but there's other ways that expansion can happen with an expansion. So let's think back to that $x equals 5 we saw earlier in my first example. How does that run? Well, the control code $x equals W needs to expand if X is unset, which means that W, to do a single step from X to whatever the result is, you need to expand W all the way. So you get some rule that, notionally looks like what I just read up there, right? W, to do a single step in step 2, I have to do many steps in steps 2, 3, 4, and 5. Those of you who do formal semantics will look at this and be like, that's not what I would write. And it's true, it's not what I write either. This is a perfectly valid rule. Reflexive transitive closure is monotonic, so it's totally okay. This rule exists. But the point I'm really trying to convey here is that everything here is really quite deeply mutually recursive, right? It's all in a big tangle. Okay, so that's the shell semantics, more or less. If people have questions or want to hear more details about anything else, I'm happy to talk about them. I'll talk about some other aspects of the semantics in a bit. This is the shell state. So the shell state sigma is up at the top. I'm just going to give you a second to sort of absorb it. I don't expect you to read the whole slide or anything, but just see what we need to keep track of. Okay, so what's going on here? This is a lot of crap. This is a huge amount of crap. So we can break it up into 3 lines in sigma. The first line is important shell metadata about how the shell is configured. What's the root shell PID? What's the process ID? You need to keep track of that for the $$ variable. Are we the outermost shell? B here is a Boolean. What shell options are currently selected? What jobs are running? What traps, what signal handlers exist? And then for funny reasons, what traps does my supershell have, maybe? Okay, then in the next row, we have sort of the current shell environment. Right, it's not less global. So it's sort of okay, what's my global environment? Or what's the value of each variable? What are my current positional arguments? What are my local environments? I'll talk more about that later on. What variable names are marked as being either read-only or exported? What are the function definitions in play? What aliases do we have? What locale am I running in? So this is information about your shell. All of this could actually be sort of changed. Right? The PID root can't be changed. Certainly not directly. But all this is sort of the current shell data. And then in the last row, we have sort of more immediate shell data. What's the current working directory of the shell? Where are we? What is the process ID of the last background command I ran? What is the last exit code that a command ran on? How many loops nested am I right now? That's important for break and continue and other control operators. And then lastly, some important hidden state for getops. And if you want to hear more about that, I can talk about it or you can see it in the paper. Okay, and then all of these structures depend on all of this sort of shell data that's really important. What's a job? What are the possible job statuses? What are the signals we could care about? All of that stuff you need to keep track of. Okay, I'll talk about that a tiny bit more. Okay, so this is the shell state. It's big, right? This is the language state that it needs to keep track of. Okay, to pop back up, I said the shell is unique. So what is unique about this? First, we've got the modal evaluation. That's unique. Next, we've got all this mutual recursion. And then last, second to last, we have these system calls and this big built-in state. We're managing a lot of stuff. And then lastly, I didn't talk about it, but the actual runtime AST that I need to support the shell includes an explicit notion of nested command loops to support reflective features like eval and source, but also other just shelly features like interactive top level and -I and stuff. Okay, so that's the shell semantics. You might at this point just be shaking your head and saying, this is hopeless. What is he talking about? This can't be the right way forward. And fair enough. there's a simpler semantics, right? All of this detail about evaluation and expansion, all of that's really wonderful, but like, it would be 100 something rules, right? It's a lot of rules if we actually wrote them down, not just in code. But the only thing that actually matters in the shell is system calls. And there's really only 18 cases you need to handle. Those are the calls that you need as the interface. So I'm hopeful that we can sort of abstract this out and sort of reason about shell from a slightly more distant perspective. Okay, that's the formal bit. Talk briefly about the implementation, and then more about sort of where I'm going. Okay, so smoosh comes in at around 11,000 lines of code. About half of that is just defining the AST and the OS model, right? It's a lot of work to get all of that sort of hammered out. Expansion and evaluation is around 3,000 lines of code. And then the built-in commands that I need are about 2.5. And there's a little bit more code for testing and various bindings. The code is all written in Lem, which is a pure OCaml-like language that compiles to OCaml so I can run code, but also compiles to things like Isabelle or Coq if I want to reason about the things. Okay, so that's the implementation. I want to talk about some problems that I encounter here. So the first problem is that POSIX underspecifies. Suppose you have a break and you have a non-empty stack. Like you're inside a function call and somebody just says break. The spec allows two behaviors, right? You could do nothing, or you could escape the call. And you might think like, what kind of spec enumerates two distinct behaviors? It's like, well, different people do different things. And like, this is why we can't have nice things. This is a disaster, right? Dash says, oh yeah, I'm just gonna ignore it. And bash says, you know what? I'm out of here. I'm gonna accept non-local break. So like, what can you do? You gotta say, great. You tell me which one you want. These are just flags you can set in smoosh. I don't know what else to do here, right? Shells are different sometimes. So this is one set of problems that the implementation encounters. There's a deeper, I think, more interesting set of problems that we encounter about flow of control. So I'm running along and so I run the built-in kill command. And kill says, oh, I want to send some signal to some process ID, right? So I kill the PID. So the shell built-in will run code that uses the OS interface to send the signal appropriately to some process. But like, what should happen? In system mode, you send the damn signal. That's the whole thing. There's nothing else to do, right? And then you let the OS sort it all out. In symbolic mode, I'm the OS. I wrote the operating system. So I have to simulate the signal send, but also the receive. So now control is sort of like a little bit tricky. So let me show you what I mean. So in system mode, if I send kill, the shell driver says, okay, great, make the system call, and then it's out of my hands. In symbolic mode, I also have to handle the signal receive. Like I could be sending a signal to my own shell and I'm the one responsible for it. So like, really, I need this diagram where like, I'm the whole POSIX model. So there's like, oops, shades of like Spider-Man pointing at himself, right? Like I have to be in charge of both. So what do I do to handle this? So I built a scheduler that works in a round robin way in symbolic mode. So in this chart, each square represents a process with its ID, dotted lines represent a fork, and dashed lines represent waits. And the way scheduling works is everybody gets to do one step at a time, and I'm gonna go round robin, right? And the first, there's only one, and then, okay, each 0 and 1 each get to take a step, and then people get to take other steps, and so on. And when a process waits on another, then I'll sort of like go out of order. So I won't always run the processes in a 0, 1, 2, 3, 4 order. That's a little too deterministic. But I'm not gonna explore all possible paths here because that's way too non-deterministic, right? That is a thing that I can't quite handle. Okay, so this is sort of the compromise that I've run into. All right, so for these last 5 minutes, I wanna quickly talk about sort of where we're at and about who cares, right? Who cares is, I think, a great question. Whenever I see a new semantics or like super cool notation, I'm like, what do we do? What do we win? What have we gotten now? And I think that there's some good like crank turning answers here of like all the cool stuff we can do, the way I'm gonna up the symbolic execution on the stepper, we'll do bug finding, like there's all this great stuff that we can do here. And that's all really wonderful. But I think there's like other higher level things we can get out of it. So this is a graph from the paper about the way that I've tested my semantics, which is, I think, really kind of the only way to talk about POSIX compliance here. So I want to draw your attention first to these numbers, where I have a single failing test on these 3 test suites. The one test I fail on Modernish. Modernish is kind of a polyfill for the POSIX shell that does some pretty wackadoodle stuff to exercise your shell. And I fail a test because Dash's parser can't handle sort of 8-bit characters properly, because it tries to steal 8-bit characters for its own parser, and that doesn't work on all inputs. And every other shell has tons of bugs in and out of their POSIX compliance modes. So to me, like maybe I'm just a really good programmer. I love that hypothesis, but like maybe this formal process we went through actually does something for us that's not just about it being a good way for dorks like us to communicate. I would, however, be remiss if I did not draw your attention to these numbers. Smoosh is slow. Yeah, about 4 times slower than other shells. And like, you know what? Fair enough, right? I run structural operational semantics. I rebuild ASTs on every step. I garbage collect, right? I'm not even trying to be efficient. All these other shells are written in C, and they mutate stuff. They're trying really hard to be fast. I'm only 4 times slower. Like, that's great. I feel great. Like, I haven't even tried yet. Like, let's see what happens when I try. So, and I think these are the other dividends, right? So, sure, Smoosh has no bugs, but Smoosh is a tool that has found bugs. It's found bugs not only in other shells and patches that have been sent to and accepted by Dash, but also bugs in the test suite. And then we saw on that chart, there's dozens of uninvestigated bugs. In the name of time, I'm actually going to skip over these bugs because you can see them in my Popple talk if you want to see them. There's sort of nothing new there, so I'm going to skip over that. And instead use the remaining few minutes to talk about where I'm headed next. So overall, I'm interested in these 5 areas: generality, improving the specification, performance, thinking about the shell design, and improving the safety of the shell for users of the shell and people who sort of have to endure users of the shell. I've got a bunch of plans. I'm really excited. I'm just getting started. I want to talk in particular about these 2 pieces of future work, thinking about the POSIX spec, and then thinking about compilation to sane languages and symbolic execution. So we already saw that the POSIX spec underspecifies, where sort of like it'll give you different choices. But sometimes the POSIX spec leaves things literally unspecified. So in the paper, in the Popple paper, I talk a little bit about there are things that the POSIX spec says, okay, this is allowed to exist, local is a thing, and I'm not going to tell you the syntax, and I'm not going to tell you what it's supposed to do, and you just all have fun and be safe, kids. Which is an attitude. That's an attitude you can have. So I think that there's work to be done here, sort of seeing like, what's the actual design space? Can we be less unspecified? Can we say what's really happening, right? There's 2 point of views you can really have here. One is that there's this bureaucratic POSIX spec, and strict adherence to it is absolutely mandatory. And this is an approach that I think has been taken in the C community, and I think it's right to do it there because portability is a huge deal, and we don't want to go back to the bad old way. We want C to be a real language where programs have meaning. The shell, people choose Zish by choice. People don't tend to end up in Zish by accident or whatever. Certainly not Osh or Fish or the more esoteric shells. So like, it's okay if there are some differences. We just need to be clear about what the scope of possibilities are. What is a portable shell script? So I've got some work going forward using fuzzing, using benchmark building, using just enumeration to try to figure out what are the precise differences these shells really express, and can we sort of find the design space in sort of a clean and clear way. I'm also interested in beefing up the shtepper, which doesn't actually do true symbolic execution, things like branching and stuff like that. I'm a little hopeful about how complicated things are here because the trade-offs are really different from, I think, more conventional symbolic execution regimes. So there's really only 2 data structures in a shell script. There's the shell environment, file descriptor, stuff like that, and then there's the file system. So you can think of that as sort of like the stack and the heap, right? The file system is your actual heap. So we have to reason about the file system, but not much else. And there's like nice work, like Philippa Gardner and her student John Insick have like nice work for reasoning about the POSIX file system. Ditto Peter Sewell with SymbolFS. So like maybe we can borrow things there that let us do what we need to do. The tricky bit, right, that we have to do that I think many symbolic executions don't bother doing is we have to handle system calls, which is to say we need to handle library code like really well. And people have had approaches for that, dealing with framework code and things like that, but it's really very challenging in conventional static analysis. And that's where we're going to have to focus all of our energies. Another thing I want to do in terms of improving safety is I want to write something that lets us take a shell script and build a program. in a more sane, more stable, more robust language out of it. So like long term, let's think about a smaller core language that manages expansion explicitly. Think about like Lambda.js is the kind of thing I'm thinking about. And then I want to reason about that core. And this is sort of where I differ from Colli, where their core has all of the Shelley bits. And I want none of the Shelley bits in my core semantics. I just want to know exactly when it happens and reason as statically as possible. But I'm actually kind of hopeful that we can translate a lot of the shell to sort of features in languages. So things like expansion can turn into explicit string manipulation. We can translate environment variables in the shell to like stack and heap variables that really use data structures. And then common commands can turn into function calls. And what's nice is we have a straightforward fallback, right? If you can't figure out how to translate it, just call system or whatever it is. Like, it's fine, right? We already can call shell scripts from programs. So just by way of example, if we look at this is taken from a grading script. What's going on? So that for loop, okay, we're reading a file, and then for every line in the file, we're munging the line with a pretty simple sed. Okay, that's a substitute or a replace call on a string. And then we enumerate every line. Okay, that could be turned into a data structure. Submitters, okay, that's a little complicated, but we can walk through it like, okay, what's it doing? We have this pipeline of translation. The first one is sort of capturing something that comes after a dash, a Z dash, excuse me. And then we get rid of a dash, turn it into spaces, and then we lowercase everything. Okay, we could conceivably have sort of like pattern matches that tell us what to do for each of those. And then if you look at the if, like, okay, that's sort of a tricky idiom, but we can see that submitters is a string with some spaces, and WC-W is counting the number of spaces in it. Okay, this is a list of strings, and we're counting the length of the list. Cool. And then we get down, let's say, to the in-script call at the bottom. And like you could try to like, okay, well, this means we need to link in a PostScript library and a PDF library. It's like, no, that's all dumb. No, just call in script if you don't know what else to do at this point. It's fine. So I'm hopeful that some form of translation here could happen and sort of help people migrate in sort of a meaningful way. Okay, and the final a couple minutes before I take questions, I want to give a couple of closing thoughts about methodology and about my motivation. So here on this slide, I have on the one side the Antikythera mechanism, which is like some cool old clock that they found under the ocean for measuring the Olympic calendar, among other things. And on the other side, we have a beautiful Roman mosaic with Plato's Academy. There's a sundial in the background, might be a little hard to see. And I want to just highlight that there's two things to think about whenever we think about any technical artifact. There's the mechanism, right? How does it work, right? And people spent a lot of time doing that for the Antikythera mechanism. And then there's the dynamics, like how do we use it? Like what role does it have in our lives, and how does it happen? And I got this distinction from Phil Agri, whose Computation and Human Experience is a lovely book. And to bring it home, I think that PL thinks a lot about programs. It thinks a lot about programmers, particularly corporate programmers, and like that kind of programming. But we don't always think about, like, we use programming languages all the time for other things, in casual ways, in sort of other ways. And I think that the dynamics here are really important, and that features that we might not like might have critical implications for dynamics. And I think that's something that we really miss in some of the hyper-technical work that we do. So I make an argument to this extent in a paper at PX, and I'd love to talk about this argument more with you. Okay, lastly, my motivation. So Americans don't have conversations. The cops don't allow it. You're not allowed to. They shut that down. So like you go to cocktail parties and like nobody actually talks. You just say like, oh, so what do you do? Do you talk about your work? It's a little depressing if you think about it. So people would ask me what I do, and like if I'm doing like the foundational theory that Nikki's talking about, I mumble something about math and then move on. It's like, oh, I'm like a fake logician, and then they're like, oh, that's cool, and then we don't talk about it again, and they talk to somebody else. But with the shell thing, I finally have a thing where I can talk to people about it. I can say, oh yeah, you know that little like terminal thing that popped up, and you like pasted something crazy in, and like that's what fixed your computer, and I'll say, like, yeah, I did that once. Like, yeah, that I work on that. That's a programming language. Like, oh wow, cool. So like everybody works on this. This is like a super important topic, right? If I've used this programming language, it must be a huge deal. And I'll say like, oh no, everybody hates it. Nobody talks about it. It's like disgusting. Everybody despises this thing. So that's part of my motivation, is to be able to have that conversation. But also there's this idea that like computing was supposed to be a revolution where we got to control our own lives better, right? Computing was supposed to make our lives better. And I don't know if you're on Twitter, but I am, and it doesn't. Computing doesn't make your life better. So something happened to that dream, right? Like I can control my computer and I can make parts of my life better using the shell and other tools. But other people, like I look at people, even savvy, intelligent people, and they can't. And that to me is a real shame. Like we've lost something in this dream. So smoosh is not the thing that's going to help them. Like we're not there yet. But like, what would it look like if we did research that could help them? Like, what would it look like if that's what we worked on, right? Rather than just addressing corporate programmers or a certain kind of development, what would it look like if we tried to have a more human computing? Okay, that's my talk. Thank you for coming. I hope everybody is doing well, and I would love to take your questions.
Thank you. So you have some questions on Slido.
Okay, cool. Let me get it open.
And if anyone else wants to ask a question, maybe write on chat or raise your hand.
Okay, great. So yeah, I'll do these just in order, I guess. So I chose LEM because originally I wanted to use SybylFS, which is Peter Sewell's model of the POSIX file system. I still haven't connected to SybylFS. LEM was not too much overhead over Plano Camel. It was annoying, right? The error messages are much worse. In particular, if you have a branch and one of the branches doesn't match the others, it won't tell you which. It just says error message. This whole branch, none of these branches match, and that's annoying if your semantics is like 1,000 lines and it doesn't tell you which one has the type error. So there's already good work in LEM. Like people have already done, I think, formal reasoning out of LEM. And I'm hopeful to use it to get to migrate to Coq. Once I have it in Coq, if I can get extraction to work well enough, I might just stay in Coq. I'm not sure. The next question is, have I considered building program logics over this semantics? The answer is yes, absolutely. Robbie Findler asked this exact question at Popple, so maybe hi, Robbie. Philippa Gardner and John Insick have a nice line of work building program logics for reasoning about the POSIX system. And I think that you could try to lift that up to try to build program logics for reasoning about the shell. I think it'd be a great approach. I'm not really an expert in program logic, so if somebody wants to work with me on that, I would love to look into it. So Leo asks, are the test suites just unit tests? Yes, they're just unit tests. I mean, they're integration tests of the whole shell, but they are unit tests. Property testing, sure, property testing makes sense. The real problem with property testing is that there's not as many properties as you might expect. Like, it's very tempting, as Coley does, to try to elaborate the shell and give it semantics in terms of some simpler core, but it's actually really hard. Every shell construct is extremely nuanced and like ever so slightly different from the other ones. So it's very, very hard to get a correct encoding of one thing as another, which is, I think, sort of a typical property testing thing. But I think property testing makes total sense. Like I have many of my unit tests are sort of like simulated property tests, where I have like, this should work like blah, and then I manually create 30 examples, which is of course just not as good. So no, I think it would totally make sense. I think working it out exactly is a tricky question. I think strictly typed shells like the PowerShell are awesome. PowerShell is like, I mean, it's in a certain sense exposing the COM or .NET internals of Windows. It's very Windows specific, right? Like it's giving you these great hooks into OS utilities in a very structured way, which is really nice. But it's also not exactly an interactive shell. Like I don't think, I'm sure there are people who could use that to do their daily work. There are sysadmins who use Python as their daily shell. But I certainly can't, right? To me, the POSIX shell is sort of where it's at. I wonder if there's a middle ground. Could we come up with some kind of typing or analysis in line with sort of the kinds of checks that PowerShell will do for a subset of the POSIX shell? There's an open source project called Oil, which is sort of doing that for Bash. It's trying to sort of like statically eliminate sort of bad moves in Bash. And it's an interesting way forward. So Piotr asks, human computing, you'd like to see everyone getting out of computing what a shell programmer can get out of computing now. And I can't tell if this is a sarcastic question or not. I'm going to interpret it in a positive way. Yes, I would like that. Look, the shell is super dangerous and error prone. It's a powerful tool. Like I have a circular saw at home and I can hurt myself with that too, but there's a lot of things I couldn't build if I didn't have it and didn't know how to use it. So to me, it's sort of like, well, look, the risk is always going to be there if people can manage their own computers, but I'd rather have people be able to manage and really be in control of their own computers and their own data than what we have now. We're like, you look at people who learn to use computers on iOS or some kind of phone interface, and they don't even know where their files are. So the moment something goes wrong, they're totally helpless. And it just makes me really sad because there's a different world where they could have known more about this and they could be more empowered. So it's just like, oh, it is a real question. Okay, cool, thanks. Peter clarifies that it is a real question. Yeah, so like I think that to me the shell is the expert's control hatch, right? Like everybody's car, like your car's hood can pop up, and like okay, it's true, you can't go into the engine, and if you could, you don't want to. But like you can change the lights yourself. You can change the various fluids. Wow, I really have been living in California too long if I'm using the car as a metaphor. But to me, that's really important. That like people I think aren't at that point for the computers, and it's in large part I think because of the systems we've designed to steer people away from these textual interfaces that offer the real forms of control we might want. Okay, I think those are the Slido questions.
Yes. We are out of time, but if there is any Zoom question, no?
Yeah, sorry if I went a little over.
No, it's fine.
Oh, will shells, plural, be part of getting there? I think so. The shell, yeah, to me, the shell to me is how an expert uses their computer.
Cool. Okay, thank you very much. It was a very nice talk.
Thank you.
I hope to be able to host you soon.
Yeah, no, I would love to come. I have such fond memories of Popple 2010 in Madrid. It was such a wonderful town. I'm really sad that I don't get to like, not that the tapas bars are open or anything, but that I don't get to go back and like find all my favorite joints and have a nice balo of tinto and oh well.
Okay, thank you very much.
Okay, bye everyone. Thanks.
Bye.